Problem number 6. A massless beam of length L is fixed on one end. A downward force F is applied to the free end of the beam, deflecting the beam downward by a distance x. The deflection x is linear in F and is inversely proportional to the cross-section moment I, which has units meters power 4. The deflection is also depending on Young's modulus E, which has units newtons per square meters. Then x depends on L according to next one. Solution for problem number 6. According to data, we have x proportional to force, y proportional to I, and also it depends from length L with the unknown power alpha, and depends from Young modulus with unknown power beta. We know that dimension for Young modulus is kilograms by meters power -1 and the seconds by power -2. Force has dimension kilograms power 1, meters power 1 and seconds power -2. Cross-section moment I has dimension meters power 4 and length has dimension meters power 1. So it means that when we use this data, we can put them in first proportion and find that we have this equation for dimensions. From here we can compare dimension for meters, that will be this one, and for kilograms, from which we can find that beta equal -1. We can put this beta in this equation for meters and find that alpha equal 3. It means that x must be proportional to beam's length L power 3. That's answer D, and this is correct solution for problem number 6. Problem number 7. A pendulum of length L oscillates inside a box. A person picks up the box and gently shakes it vertically with the frequency omega and the fixed amplitude for a fixed time. To maximize the final amplitude of the pendulum, omega should satisfy next value. Solution for problem number 7. In the frame of the box, vertical shaking is equivalent to having G oscillate with the frequency omega. To increase the amplitude, gravity should be strong when the pendulum is moving down and weak when it is moving up. So because it happened twice, when the pendulum moving down and moving up, there must be 2 oscillations per oscillation of the pendulum. So we have omega must be equal 2 times square root from G over L, which is answer A. That was the solution for problem number 7. Problem number 8. The coefficients of static and kinetic friction between a ball and the horizontal plane are μs equal μk equal μ. The ball is given a horizontal speed, but no rotational velocity about its center of mass. Which of the following graphs best shows the rotational velocity of the ball about its center of mass as a function of time? Solution for problem number 8. The kinetic friction force, μ multiplied by normal force, applies a constant torque, so the angular velocity initially increases linearly. After it begins rolling without slipping, the angular velocity remains constant. If we check all 5 possibilities here, only graph C showing this behavior for angular velocity. Initially it's linear and after it's constant. So that's the correct answer for problem number 8. Problem number 9. A 3 kg ball moving at 10 meters per second east collides elastically with a 2 kg ball moving 15 meters per second west. Which of the following statements could be true after the collision? Solution for problem number 9. We can see that total momentum in the initial frame of reference is 0. It means that it must be 0 after collision too. And also because we have a absolutely elastic collision, speed of each ball must be the same as before collision. Only direction could be different. If we assume this possibility, we can see that only in case E we have this possibility. In that case, the ball with a mass 3 kg must move directly to the north with a speed 10 meters per second. And this is correct answer E. And it was a solution for problem number 9.